When asked to find the average rate of change of a function, what we'll notice is that when calculating that, we're actually calculating the same thing as the slope of the line that connects 2 points on a particular function. The average rate of change formula is given here, but if you'll recall, the formula for calculating the slope between 2 points is rise over run. And when we have two ordered pairs, we take the change in the y values and then divide that by the change in the x values. Well, when we have a function, let's also recall that a function has an output that is a y value. And so this slope formula can be rewritten substituting functional notation in for each of these y values. So this first y value is the output that is generated when we plug x sub 2 into the function, and the second y value is the output generated when we plug x sub 1 into the function. So this in the top of the fraction is y2 minus y1, and then in the denominator still x2 minus x1, and again that is our average rate of change formula. So the average rate of change is giving us the slope of a line that connects two ordered pairs. So in this example, we are asked to find the average rate of change, and as a reminder, that's the same thing as the slope, but we're given two x values, not two ordered pairs, but we're also given a function. So in order to calculate the average rate of change, basically we need two ordered pairs so that we can calculate the change in y over the change in x. What we currently have are two x values, so we know that x is equal to 1 is going to be the x-coordinate of one of the ordered pairs, and x is equal to 2 is the x-coordinate of the other ordered pair. To determine the corresponding y values, what we'll do is we'll take that x-coordinate 1 and plug it into the function to determine its corresponding y value. And similarly, we'll take x is equal to 2 and plug that into the function to determine its corresponding y value. So let's evaluate the function at 1. When plugging anything into a function, my recommendation is that you open up a hole for all of those independent variables into which we're going to plug the ones. So this is x squared plus 2. Whatever is indicated inside the functional notation is what gets plugged into that independent variable. So we have 1 squared plus 2, which is 3. And now we can replace this y-coordinate of the ordered pair with what we found it to be, which was 3. So let's do that again and determine the y-coordinate of the second ordered pair by plugging 2, this designated x-coordinate, into the function to determine its corresponding y value. Again, we'll open up a variable hole for the independent variable. So this is x squared plus 2, which is of course again the original function. And we're going to plug in the 2 into the x variable spot and determine what its corresponding y value is. So now we have 2 squared plus 2, which is 4 plus 2, which is 6. And 6 is then the y-coordinate that corresponds to the x-coordinate 2, and therefore completes the ordered pair. So we said we needed two ordered pairs, and now we have that. The formula for the average rate of change formally is the function evaluated at the second x-coordinate minus the function evaluated at the first x-coordinate divided by x sub 2 minus x sub 1. But it might be easier to think about that as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, since we are so familiar with the formula for the slope. So we can calculate this average rate of change simply by calculating the slope between these two ordered pairs. So we'll say y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1, so we've got 3 divided by 1, and the average rate of change here is just 3. 3 is also the slope of the line that connects these two ordered pairs. Let's now come down and graph the equation of the function that we started with, which was x squared plus 2. X squared plus 2 is a parabola that opens up with a y-intercept at 0, 2. We also know that it has the ordered pairs 1, 3 and 2, 6 on it. We can go ahead and use the fact that we know f at 1 is equal to 3 and f at 2 is equal to 6 to give us these two ordered pairs. We also know that this graph is even, and so the ordered pair negative 1, 3 and negative 2, 6 would also be on the graph. And so we can connect the dots here and graph this parabola. Now we're asked to find the equation of a secant line. A secant line is one that passes through the function, and the line in particular that we're looking for is the one that connects the two ordered pairs 1, 3 and 2, 6. So I've done my best to draw this secant line. It's not perfect, but I think you get the idea. And we want to find the equation of this line here. Remember, in order to find the equation of a line, we need two things. We need the slope of the line, and we need any point. We've already found the slope of the line to be 3 because remember the average rate of change is the same thing as the slope. And any point we can use either the ordered pair 1, 3 or the ordered pair 2, 6. I'm going to use 1, 3 since the numbers are smaller. After we have our slope and any point on the line that we're looking for, again that's the secant line here, we can then plug these two values into the point slope formula. Y minus y1 is equal to m times x minus x1 and write the equation of that line. So we're going to plug in 1 for x1 and 3 for y1. And 3 also is going to be plugged in for the slope. So we'll have y minus 3, which is the y-coordinate of the point, is equal to 3, which is the average rate of change, or the slope that we calculated, times x minus x1, which is the x-coordinate of our point. This is the equation of that secant line. We would consider this to be in point-slope form. But if we wanted to write this in slope-intercept form, we would distribute the 3 into the parentheses and get y minus 3 is equal to 3x minus 3 after that 3 is distributed in. And then we'll add 3 to both sides to completely isolate the y and get y is equal to 3x plus 0, which of course doesn't have to be written. So y is equal to 3x is the equation of that secant line. Notice y is equal to 3x is going to have a y-intercept at 0, 0, and it does look like our secant line would be passing through the origin as well. So this equation does appear to be the secant line that we were after.